Hello friends, I welcome you in lecture number 29 on relations. In this lecture we are going to discuss about partition and covering of a set, which is going to be useful in upcoming lectures on relations. So first we understand with the help of example, and then we will define what is partition and covering of a set. Suppose I consider this set having say 5 or 6 natural numbers 1, 2, 3, 4, 5, 6, and I want to decide partition and covering of a set S. So I am considering subsets of S. For example, say A1 equal to 1, 2, 3, A2 equal to say 4, 5, and A3 equal to say 6. So this is one collection of subsets of S, and I am considering another collection also. B1 equal to say 1, 2, 3, B2 equal to say 3, 4, and B3 equal to say 5 and 6. Now if you observe for second collection as well as for first collection, that if you take union of all these three sets, then you will obtain set S. Similarly here B1, B2, B3 are also subsets of S, and their union is this given set S. So we are considering subsets of given set, and the union of those subsets is set itself. For example, if I consider union of A1, A2 and A3, then I obtain that this is equal to S, and all these A1, A2, A3 are subsets of S. Similarly, union of B1, B2, B3 is also equal to S, and all these are subsets of S. So we can say that this A1, A2, A3 cover this set S, or this collection of A1, A2, A3. If I consider this set capital A equal to A1, A2, A3, then set A is a collection of subsets of S. And suppose I consider another collection as B1, B2, B3, then set B is also a collection of subsets of S, and both these collections are in such a way that union of all the members of that collection is equal to given set S. Same thing here, union of B1, B2, B3 is equal to S. So whenever this happens, then this type of collections are known as covering of a given set. Covering of a set S. Here set A or collection A and collection B both are having their members as subsets of S, and a union of the members of both the collections is equal to set S. Therefore these collections A and B are called covering of S. And if you notice, for this first collection, if I consider this type of pairs and take their intersection of A1 and A2 is empty set, there is no common element. Similarly, A1 intersection A3 is also an empty set. A2 intersection A3 is also an empty set. So I can say that these A1, A2, A3 are mutually disjoint. If I take intersection of any two of these three sets, then their intersection is empty. Therefore these sets are mutually disjoint. And here we can see that B1 and B2 are not mutually disjoint, because there is one common element 3 in B1 and B2. Therefore their intersection is not empty. So in addition, if our members in the collection are mutually disjoint, then in that case we obtain a partition of a set. For partition we require one extra condition, and that extra condition is that all the members of the given collection are mutually disjoint. So this set or collection A is a partition of a set S, but this collection B is not a partition of set S, but of course it is a covering. So here A and B, both the collections are covering of a set S, but set A is a partition of a set S, set B is not a partition of a set S. So for partition we require one extra condition, that members of the given collection are mutually disjoint. So these two are very simple definition. We again recall, suppose we have a set S. Now suppose I consider A1, A2 up to say m elements. Suppose I consider this collection A, and this A1, A2, Am are subsets of a given set S for each I equal to 1 to up to m. Suppose each AI in this collection is a subset of S, and union of all these sets A1, A2 up to Am is equal to given set S. Then in that case this collection of subsets of given set S is called a covering of a set S. Now if we have one more condition satisfied in addition to this condition, if we have members of the collection are disjoint, that is if we take any two members from this collection, then their intersection is empty, then this collection is called partition of a set S. So here this A1, A2, A3, this collection is covering as well as partition of a set S, but this collection is only a covering of S, it is not a partition. So now it is obvious that for partition we require one more extra condition, and it is clear that every partition is a covering of a given set, but every covering may not be a partition. Here this collection B is a covering of this set S, but it is not a partition because its members are not mutually disjoint. I have written this definition here. They can ask you to write down the definitions also. First I have written the definition of covering of a set. Let capital S be a given set, and suppose we have this collection of subsets of S, A1, A2 up to Am are subsets of given set S, and their union is set S, that is A1 union A2 union and so on up to Am. This is equal to S. Then the set A or collection A is called a covering of S. This collection is called a covering of S. And for partition we require one more condition. So remaining things are as it is, and extra condition is that if we take any two members in this collection, then their intersection is empty set, that is all the elements of this collection are mutually disjoint. So if this extra condition is satisfied together with this condition, then the set A is called a partition of a given set S, and whenever we have partition, then these members A1, A2 up to Am are called blocks of the partition. The members of the partition are known as blocks of the partition. And I am taking one more example to explain this partition and covering. Suppose we have a set S containing these three alphabets A, B, C, and we are considering different collections of subsets of S, and we will decide whether those collections are partition or covering or both or neither. first collection is set A having these two subsets of this set. You can see that this set AB is a subset of S. This set is also a subset of S because its elements are B and C, which are also members of S. And if we take the union of these two sets, then we will obtain capital S. So it is a covering of S. But if we take intersection of these two sets, then you can see there is one common element. So these two sets are not mutually disjoint. Therefore, this collection is not a partition of given set S. This is another collection. Both these sets are subsets of given set S, and if we take union of these two sets, we will obtain this set A comma C, but this is not equal to S. Therefore, this is not going to be a covering of S, as well as it is not a partition of S, because union of the members of this collection is not equal to S. Here B is missing. So this collection is neither a covering nor a partition. Here we can see that if we take union of these two, then we will obtain given set. So this is a covering, and there are only two members. If we take their intersection, then we will obtain empty set. So this is a covering as well as partition of a given set S. Here we have only one member, and that is nothing but set itself. So this is equal to S, and because we have only one member, we can say that elements of D are mutually disjoint, because we cannot find out two subsets which are not mutually disjoint. So this is by default a partition of a set S, but there is only one block in this partition, and that block is nothing but given set itself. Here we have two blocks in this partition. We are having two blocks, set containing A and set containing BC are blocks of the partition, this partition C. Here we have partition containing only one block, and here we have three subsets. If we take union of all these subsets, then we will obtain set S. Therefore this is a covering of a set S. And if we take intersection of any two sets in this collection E, then we will obtain empty set. Therefore all the members of this collection E are mutually disjoint. Therefore it is a partition of a set S. And here we have three blocks, set containing A, set containing B, and set containing C. So among given partitions, this is the partition having maximum number of locks. There are three elements in a given set S, and we have taken singleton sets containing all these three elements, and they give us the partition of a set S. So we can say that this is the biggest partition of a set S, and as we have seen, the smallest partition is the partition having only one block, and that is nothing but set itself. And this is true for any finite set. Suppose I have a set S having say m elements, then the biggest partition is nothing but set containing A1, A2 up to AM. So there will be m blocks in the biggest partition of this set S, and the smallest partition is nothing but set itself. If you consider this partition or this collection, in this collection we have only one set, and that is set itself, then this is the smallest partition for given set S. So it is very easy to understand partition and covering of a set. Here also we can see, if we take union of all these members, then we will obtain given set S, Therefore this is a covering of set S. But you can see these two are not disjoint and these two are also not disjoint. They are having some common element. Therefore this collection F is not a partition of a given set S. And these are some remarks which we have already discussed. Every partition is also a covering, and converse is not true. Every covering may not be a partition. If we have any finite set, then the smallest partition consists of the set itself as a block, while the largest partition consists of blocks containing only single elements that we just discussed. So this is all about this session. In this session we have discussed the definition of partition and covering of a set. And let me recall again. Suppose I have some set S and I am interested about covering of this set S. Then covering of a set S is the collection of subsets of S, say A1, A2, Am, such that union of all these subsets of S is equal to S. And partition means we require one more condition, and that condition is that all the members of this collection are mutually disjoint. So every partition is a covering. So this is all about this session. I hope you like it. Thanks for